Students, next we are going to discuss about that springs connected in series. So there are two ways are connected in springs. The one is the series and another one is the parallel. Suppose if the two springs are connected in series, what is the effective value of this spring constant? Suppose the two springs are connected in parallel, what is the effective value of spring constant? That spring constant is more. You can apply the force will be also more to elongated or compressed to the spring. If the spring constant value is less, you can apply it needs only a very less force for elongated or compress that spring. Okay, do you understand? So spring constant F is directly proportional to F is equal to minus Kx. That is the Hooke's law. So here X value is a constant. Okay, so X value you can you can imagine this is the constant. So force is directly proportional to K. When you apply, when the spring constant value is larger, means it needs more force for elongated or compress the spring. If the force constant value is very less, means only a very few force. When only a very small amount of force you can apply that for elongated or compress that spring. Okay, do you understand? Now, if the springs are connected in series, so what is the spring constant value? So, series connection means one spring, this is the one spring, that spring value is K1, the spring constant value is K1, and another one spring, that spring constant value is K2. So, both the springs are connected in series means one end of the spring is connected with another one of the spring. Okay, so another one end spring is connected with one mass M. Now, so this will be an equilibrium position. So that is the X naught. X naught is the equilibrium position. Now you can apply that force. You can apply the force. So what happened? So if it will be moving back and forth for its about their mean position. So that force is F. That F value is equal to minus Kx. Minus Kx. Okay. So this is the net force. So this is the net force constant value. And X is the net value. Okay. So net displacement how much? For first spring. First when you apply the small amount of force, that first spring will be elongated or compressed some distance. That distance is x1. And the second spring also elongated or compressed x2. Because both the springs are having different force constant. Both the springs are having different force constant. So only x1 and x2. So both are displaced different displacement. Okay. So first one, F is directly proportional to minus K1 x1, and second spring, that also minus K2 x2, because both are applying a very same force only. So only I can put that same value, F is equal to minus K1 x1 and F is equal to minus K2 x2. Okay. Then next, F is equal to minus K of x1 plus x2. F is equal to minus K of x1 plus x2. So K is the net force if the springs are connected in series. So F is equal to minus Ks. So F is equal to minus Ks of x1 plus x2. Okay. Then x1 plus x2 is equal to F by minus F by Kx. Okay. So x1 plus x2 is equal to minus F by Ks. then k minus k1 x1 plus x2 is equal to minus f by ks. So this is the equation number 1. From this equation, k1 f is equal to minus k1 x1. From this equation, you can get x1 is equal to minus f by k1. And from this equation, x2 is equal to minus f by k2. Okay, so this is the net force acting on the system. Net force acting on that springs are connected in series system. So Ks represent the springs are connected in series. So Ks of this displays this some different displacement. So x1 plus x2. So you can sum up these two displacement. This is the x1 plus x2. From this equation, you can rearranging that equation. We can get x1 plus x2 is equal to minus f by ks. Okay. So x1, what is the value? x1 is equal to minus f by k1. Then next x2 is equal to minus f by k2 is equal to minus f by ks. Okay. So minus sign, you can divide with minus sign, all are having, so just you can cancel them, or you can take that minus f. From this equation you can take them out, minus f. So 1 by k1 plus 1 by k2 is equal to minus f by ks. Minus minus cancel, and f cancel. You can get 1 by ks equal to 1 by k1 plus 1 by k2. 1 by ks equal to 1 by k1 plus 1 by k2. So if the springs are connected in series, the reciprocal of effective or total spring constant is equal to the sum of reciprocal of individual spring constant. Okay, so that value is, if the resistors are connected in series, that effective resistance value is always lesser than the individual spring constant. Okay, do you understand? For example, k1 is equal to 1 and k2 is equal to 2. Okay, so you can substitute that. 1 by ks equal to 1 by 1 plus 1 by 2. That's equal to 3 by 2. 1 by ks equal to 3 by 2. Then ks equal to 2 by 3. That value 0.666. So here k is equal to 1 and k is equal to 2. So that effective spring constant value is lesser than the individual spring constant. Okay. So if the springs are connected in series, we can get that very less spring constant value. Okay. Or stiffer constant value. Okay. Do you understand, ma? Then next, here I can take that only two spring springs. So that spring constant is k1 and k2. If I take that n number of springs are connected in series, what is the effective? What is that effective or total spring constant? So 1 by ks equal to 1 by k1 plus 1 by k2 plus 1 by k3 up to 1 by k nth spring. Okay. So R summation of I is equal to 1 from n 1 by ki. Okay. Do you understand? Suppose all that values are equal up to kn is equal to k. All the spring constant values are equal. What is the total? This is total spring constant. So there is 1 by ks is equal to n number of springs divided by k. Okay. So n divided number of springs divided by k. Then ks is equal to k by n. Ks is equal to k by n. Okay, do you understand? That's all. So if the number of springs are connected in series combination, n number of springs, n number of equal springs are connected in series combination, the effective spring constant value is equal to k by n. Okay, ma? Do you understand? Okay, thank you.